The concept of effective stress assumes that the soil mass as an equivalent continuum. It appears as a very simple concept, equation. However, it can be surprisingly tricky, and throughout this presentation and the next one, I would like to present several cases to make sure that we understand effective stress. The whole story starts with Archimedes when he sat on the bathtub and he felt lighter because of the effect of buoyancy being equal to the weight of the fluid displaced by the body. That is really the beginning. But let's explore now a more interesting case relevant to us in the geotechnical field. Let's assume that I have this body with a certain weight, and we are trying to pull it, and the goal is to assess the force T that is required to displace the weight. Well, in the simplest of all cases, the force T is going to be equal to the friction coefficient times the weight. However, the story can get a little bit more interesting if in the space beneath the weight, all of a sudden we begin to pressurize it either with air or water, and that fluid begins to come through the pores, and so there is all of a sudden an uplift force U that acts against the weight. In this case, this was the dry case. In the case that there is this pressure from underneath, like an artesian pressure, then the force, the ultimate force that is required, not just any shear force, the ultimate shear force to displace the body will be the coefficient mu. However, it won't be the whole weight, but the weight minus the U force. Because friction happens only between mineral, the fluid itself is viscous, it's not frictional. And so this is a lighter weight, like a buoyancy force, but now driven by that force U. Clearly, we could divide everywhere by the area, apparent area of the body, and then this equation becomes that tau ultimate is equal to the total weight of the system minus the fluid pressure, now this is pressure, times mu. Now if we plot this in a tau sigma space, that mu becomes the slope of the line, and so this is tangent phi, which is the same as mu. What this is telling us is that the shear strength is determined by the effective stress that is carried throughout the mineral skeleton. And so we are going to call this quantity what is effectively felt by the mineral skeleton, and this is sigma prime. Therefore, sigma prime is equal to sigma minus U, and that is Terzaghis effective stress, taken from the point of view of strength. But the same effective stress is going to determine stiffness and dilatancy with pretty much the same conceptualization. So let's explore this Terzaghis effective stress a little bit further. Let's explore the concept of effective stress now at the particle level, and imagine that we have a rigid chamber where we can hang from the top two particles in such a way that they are touching each other, and furthermore I'm going to put a spring in between them against the boundary, between the particles at the boundaries. Clearly the force exerted by the springs is also felt at the contacts. Now imagine that I connect this to a pump and that I increase the fluid pressure around the particles. And now, if I look at the fluid pressure around the particles in a non-gravitational system, so it's the same from all the angles, top and bottom, you see that the top and the bottom cancel out, the left and the right. If the contact is a point, the left and the right integrate to cancel out as well. So that means that I increase the fluid pressure, yet the effective force felt between the particles, let's call it force N prime, remains constant. We wonder what is going on with effective stress. I have increased the fluid pressure, but I have not changed the effective force between the particles that was caused by the springs. This is really surprising because it appears to violate Terzaghis effective stress. We can go one step further and let's consider the following situation whereby we also have a rigid container chamber and we put lots of grains in contact with each other, and we are going to surround this with a latex membrane like we do in the triaxial test. And we connect the inside of this membrane to a pump where we control the fluid pressure, and from outside we also apply a fluid pressure is from the outside, so we are going to call this one the sigma confinement. And if we magnify the situation next to a particle, this is the membrane, this is a particle, the fluid from inside is applying U, the particle is applying a constant force, a contact force N, and the fluid is applying U, and from here I have the sigma confinement. So now by force equilibrium, we realize that the sigma confinement, or let's say from the left, that the force per unit area, so or we multiply this all by area, or we divide by area. Let's multiply everything by the area. The force carried by the particles plus the pressure times the area is equal to the sigma confinement times the area. If we divide everything by the area, the force carried by the particles, the Skeletonian forces, become the effective stress plus the fluid pressure is equal to sigma confinement. Therefore, sigma effective is equal to sigma applied at the boundaries minus U. And now we do go back to Terzaghis effective stress. And in fact, either I increase the confinement at the same pore pressure, so the effective stress increases, or I increase the pore pressure while maintaining the confinement constant, and the effective stress decreases. So this is working right. Now we have to think, how come the case on the left seems to violate Terzaghis, however the case on the right seems to be working? And the point I'm trying to make is that effective stress doesn't emerge at the particle scale like it is on the left. The point I'm really trying to highlight is that effective stress gets established at the boundaries where this force equilibrium can be invoked. For the case on the left to be true, we assume that the point of contact was very, very small. And in fact, that also applies here. The point at the contact is very, very small. So there are a couple of assumptions here that I'm going to come back to review with you. You can certainly recognize the fact that we do have boundaries in a triaxial test where the grains have a latex membrane between the sediment and the confining pressure. We don't have such a situation in the field. There are no membranes, except in the case of an aquitard. And so what is going on? Well, imagine that we have a cut-off wall, and we have flow lines. And if you draw the flow net, then each of these equipotential lines is actually equivalent to a boundary. Because notice that I can do a derivative with respect to space, and so the change in sigma prime with respect to x is equal to the change in total stress with respect to x minus the change in pore pressure with respect to x. So every time I have a gradient in pore pressure, I will have a gradient in effective stress if the total stress remains constant. And you may wonder why that is the case. Well, because I'm losing pore pressure by dragging against the grains. So the fluid is moving and is dragging itself against the grains, and as it drags against the grain, it's transferring that energy onto the grain skeleton, and now it's being picked up as effective stress. In the previous analysis, when we were integrating the pressure around particles to show that effective stress doesn't emerge at the particle level, we were saying that particles were contacting at a single point. Therefore, that point itself was not affecting the integral around the particle. However, this is not the case if particles have been squeezed enough so the contact is a flat, large contact. When does that happen? That happens when either the mineral is very soft or the stress is very high. And so we need to make a correction for Terzaghis effective stress when we go deeper into the ground, for example, for CO2 geological storage, for petroleum and gas geomechanics. This was recognized earlier on by Biot in 1941, and as well by Skempton in about 1960s. And their solution is as follows. This is Terzaghis effective stress, but we're going to make a correction for the size of those contacts. And that is a correction alpha, where alpha is equal to 1 minus the bulk stiffness of the granular skeleton over the bulk stiffness of the mineral. Notice that in the near surface, the granular skeleton can deform much more than the minerals can, volumetrically speaking, and so this quantity goes to 0, alpha is 1, and we return to Terzaghis effective stress. At greater depth, now the stiffness of the skeleton, because of confinement and the contact flattening and pressure solution precipitation, the stiffness of the skeleton now is significant with respect to the bulk stiffness of the mineral. So this is now, the number 1 is beginning to decrease, and therefore, in the distribution of who carries the load, the pore pressure or the skeleton, now alpha begins to tell us that that balance is changing because the contacts are becoming wider. So this is a modification of effective stress for the stiffness of the skeleton, and if you follow the line of Biot, this is poroelasticity, poromechanics. There are other situations that we would like to recognize next. Imagine the following condition where we have a membrane holding particles, and this is going to be an esoteric case, but it will paint the right picture, and we have the particles everywhere. Internally, we are going to control, this is partially saturated, so we are going to control the pressure of air, while at the same time, we have a sigma confinement. Now, as we said before, effective stress gets established at the boundary. If I increase the air pressure, I'm pushing the membrane away, decreasing the effective stress. So now we can say that effective stress is equal to sigma confinement, the total at the boundary, minus U air. And so far, we are okay with that. But let's assume that internally, there is a partial saturation, and so somehow there are menisci here that are holding the water in tension. So the pore space in the central part, I'm going to say that it is under suction. This part of the granular medium that is partially saturated with the pore space and the suction, now it experiences the skeletal effective stress being transferred from the boundary plus the capillary suction. And that capillary suction is the pressure difference between the air and the water. Recognizing that the water is under lower pressure because it's being put in tension by this menisci and the interfacial tension at these edges. Now, because this is not happening over the whole body, this is going to be a fraction of that suction which is going to be controlling this. And this is Bishop's effective stress. And this comes from 1959, 1961. There are a couple of notes and articles around that time. In summary, we have something that is created at the boundary, sigma minus U air, and something that is happening internally, which is the suction. And by the way, I could also connect by a porous tone, a high air entry value porous tone, and actually control the U water. So I can control these two separately. Notice that when the system is totally saturated, psi goes to 1, and mu air, the pressure of air cancels out, and we fall back to Terzaghis effective stress. However, as the soil is getting drier and drier, the effect of suction is taking place more locally, and so psi is going to decrease. So as a first order approximation, this is pretty much similar to the degree of saturation. If we adopt not an induction approach to proving concepts, but a falsification approach, in other words, we need to provide only one example to show that this doesn't work, then we are invited to identify a soil condition whereby decreasing the suction, the soil doesn't swell, but it contracts. How could that be the case? Well, that is the case of loose soils such as loess, and when it rains, the suction decreases because the degree of saturation increases, yet the soil collapses. With that example alone, we know that Bishop is not fundamentally correct. Yet, it is probably the most extensively used expression in unsaturated soil behavior because it works conveniently in a large number of cases, but please remain very cautious that it has been falsified. So this is the addition of capillary forces. Other forces that we were talking about in the other presentation on particle level forces were electrical forces. In particular, the double layer repulsion and van der Waals attraction. And it is very easy to prove that these do exist. For example, if you take a test tube with kaolin and with a kaolin suspension, and you put it in a centrifuge, and then by the time you stop the centrifuge, you tip the kaolin plug that has formed upside down, still fully saturated with water, and it does never fall down. That means that there is indeed attraction. Particles remain there in the plug at the top, even though they are heavy. How could that be the case? Well, because this van der Waals attraction, once the particles became very close to each other, will hold the weight of the particles. And so there are several alternative forms of this equation. For example, we could say that sigma effective is equal to sigma minus u, Terzaghi, minus repulsion minus attraction. And so we take into consideration the double layer repulsion and the van der Waals attraction. Now, in order to explain that, we are actually having to create a fairly weird configuration, like something like this, where particles are both transferring effective stress through contact, effective mineral to mineral contacts, while at the same time they are experiencing DLVO attraction and repulsion in this other part of the particle. And that is difficult to conceive, except that we could recognize that in a complex granular fabric of fine-grained sediments, some of them will be edge to face aggregated, let's say. In other parts may be dispersed, and so it will be a mixed, statistical mix of all these. But by the time we go to bentonized and very dispersed materials, remember the regime of pH where materials are dispersed and particles are separated like that, there is actually no interparticle contact. So all the effective stress that is applied is actually going to be taken by the repulsion between particles, and this could be the other explanation. And there is one more in between, and so you will see several names and associated with this, from Lamb to Sridharan. I can also find examples. I need just one example. It works in many cases, but I need one example to show that these are not correct. And for example, if I take a kaolin paste or a bentonite paste and I change the pore fluid concentration, under certain conditions I get exactly opposite effects on the behavior of the material. Therefore, there is something that this is not properly capturing. So what is going on? To summarize, we have Terzaghi's effective stress, and then we have modifications to Terzaghi's effective stress, which we're going to put in the following form, minus or plus some modification, which is a function of either capillary, electrical. If you are working with magnetic particles, you could put here magnetic. And in all cases, whether we talked about capillary forces, for example, Bishop, or if we are talking about electrical forces, Bolt, Lamb, Sridharan, and Rao, or magnetic, I cannot think of any author that has used them in this format. In all those cases, we were able to identify special cases that would falsify this formulation. So there have been lots of efforts, people coming from advanced mechanics and thermodynamic analysis, etc., to try to create formulations which are more robust. Early work by Fredland and Morgenstern in the 60s actually recognized that these two were of a different nature, and it was better to talk about a certain property, for example, strength or stiffness, some property, in terms of sigma minus u, and in terms of these other components, R minus A or U air minus U water. And why is that the case? This is established at boundaries. However, these ones are taking place locally, at contacts, in the extreme case of low saturation, for example. And so these are two completely different actions on the soil, and they have marked differences. And so we have to think of as two different linearly independent actions in a space. There are different vectors in the base that determines soil behavior. So it is worthwhile to think of these two separately, not to add them up as two coexisting scalars. And so to put here the boundary effects, and here the contact level. And if we do that, the formulation gets a little bit more complex. The simplicity of this formulation is what makes it so valuable. It makes it more complex, but it allows us to properly capture the different actions governing the properties and the behavior of soils.